Okay, so in the last video we saw that as we changed the number of compoundings, our interest kind of kept creeping up. When we went from compounded annually to compounded monthly, we gained an extra $7.42 in interest. And the question is there an upper limit of how much interest we can get? So increasing the number of compoundings, increasing the number of times interest is compounded from 1 to 12 netted us $7.42 in additional interest. As we increase the number of times the interest is compounded per year, the amount increases. So the question becomes, if we increase the number of times interest is compounded without bound, how much more can we earn interest? So let's consider the following. I'm going to make a definition. I'm going to let H be equal to N over R, which implies that R over N is the reciprocal of H, and N times T equals N over R times RT, which is H RT. So if we replace this R over N with 1 over H, and replace NT by H times RT, we can then rewrite this as a power. And we want to specifically focus on this expression inside here. And as we increase n without bound, making it larger and larger, h is going to increase without bound. And this gives us a special number that occurs in nature. It's the natural base e. And number e is an irrational number, kind of like pi, 2.7182a blah 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 blah. It comes from examining this behavior as h increases without bounds. It goes to infinity. So as I make h larger and larger, this value gets closer and closer to this value of e. Now it's going to be important for us to be able to calculate this on our calculator. So on your calculator you should have an e to the x key. So if we look at our TI-30 XS key, we look at the third key down from the second key, we see this ln key, and in green is the e to the x key. So we're going to have to hit second and hit the ln key to access that. So if I look at on our workbook on page 115, if I need to enter e to the 4.3, what we do is we do our second key and then the ln key. And notice it gives me e, and it's already shifted my cursor up to the exponent. So I can just type in 4.3, hit enter. And let's round it off to 4 decimal places. So that'd be 73.6998 if we round that off. Okay, in my last plus, just see where they want you to round that off to. Now to do 3b, I'm going to do the same thing. Now I'm just going to type the 2 first. Second, ln, whoops, I had the wrong key, so let me try that again. 2, second, ln. Notice my cursor is already up there. Type 3, hit enter. So that'd be 40.1711 if we round that. Alright, so let's see how this involves with the problems we've been working on. So if we go back to that example 2 where we kept increasing the number of compoundings, so increase without bound, the amount that would have been in the count would have been 10,000 e to the 0.04 times 1, which would give us $10,408.11. So we do have an upper limit of how much interest we can get. And the way we'd enter that in our calculator, here we type in 10,000, second, ln, 0.04 parentheses 1. Hit enter. And then they're rounding off to the nearest cent. Now, when we have an infinite number of times interest is compounded, we say that the interest is compounded continuously. So interest compounded continuously, so that P be the principal, that's our present value, is invested at an annual interest rate R, compound continues for T years. The amount A future value will be A equals PE to the RT, or R has been converted to a decimal. So if we look at problem number 4 on page 115 or workbook, Maria invests $3,000 in account that pays annual interest rate of 5% compound continuously. How much does she have in the account after 12 years? So we're doing, if I can get my variables correct here, A equals PE to the RT. Our principal is 3,000. Got to write that R as a decimal, 0.075, and then T is 12. And then we're just going to pop that into our calculator. Rounding it off, we would say that's $5,466, and we'll go with 36 cents. Since the place to the right of the 5 is 6, I have to add 1. It's 5 or higher. Let's try the next one. Alyssa has $5,000 that she can invest for 6 years in one of 2 accounts. The first account pays 8% interest compound quarterly, and the second pays 7.92% compound continuously. Which one's a better investment? For the quarterly, we're going to have to use A equals P, 1 plus R over N raised to the NT. For the continuously, we're going to need to use A equals PE to the RT. So let's plug in our values. So the first count is 8% compound quarterly, so we have $5,000. 8% would be 0.08 over 4 raised to the 4, and number of years is 6 years. Alright, so let's clear this. Let's put that in our calculator. And then hit enter. And again, I'm going to just round it off to the nearest cent. So it'd be $8,042.19. Now let's do the second one. So principal is still $5,000. We have a slightly different interest rate. So 0.0792. Time here is 6 years. So now we're going to plug that in. Then we're just going to hit enter. And rounding that off, that'd be $8,041.68. So the first investment, so the first account, is the better investment. Because you get slightly more money with it.